A very good morning, students. The last class we have seen about the basic concepts in the electromagnetic fields. We will be continuing the same concept and we will be applying it to the special areas. Okay. So these are the things what we have seen in the last session about the different coordinate systems. About the different coordinate systems we have seen. Then we have seen about the transformation of coordinates in electromagnetic fields. Later on, we have entered into three important topics: gradient, divergence, and curl. Gradient, divergence, and curl for different coordinate systems. So that we have taken in the last session. So now we will be seeing about the electric field and basic introduction about Coulomb's law and electric field. We have seen it on the last session. So now we will be applying that basic laws what we have studied in the last class to the special applications. About these problems also we have seen, and I have told you about the difference in gradient, divergence, and curl. So these are the things what we have seen in the last thing about the principle of superposition of charges. That we have point charge. If we have several point charges, we can find out the electric field because of that several point charges. And the problem also we have seen. So the next one we can go for the line charge. When you go for the line charges, we have a different thing. We have line charge density and surface charge density and volume charge density. The line charge density is given by the formula charge per length. Similarly, surface charge density is given by the formula charge per area. Okay, so in the data, in the problem, they will with the unit only we can find out whether it's a surface charge density or line charge density or volume charge density. When you go for the volume charge density, it is charge per volume. Charge per density, volume charge density is charge per volume. So Q by V, that what we will be having as Coulomb per meter square. Okay. So the first one, you can find out the electric field due to charge uniformly on an infinite and finite line. You can see that one, the diagrammatic view. Okay. So the line charge is having of length L. Because of that line charge, what will be the electric field at the point P? What will be the electric field at the point P? That we can determine. Okay. So if the line is, this is of line is of finite length. If it is of infinite length, what will be the electric field at the point P? So that what we have this concept as electric field due to circularly charged line, finite line and infinite line. For the finite line, we have along two concepts. Along the x-axis, if you measure along the x-axis, the electric field intensity along the x-axis is given by the formula rho L by 4 pi epsilon h into cos alpha 1 plus cos alpha 2. Rho L is the line charge density. Okay, and h is the distance between the point and the line charge. The diagram you can see that one. H is the distance between the point and line charge. Okay. So along the x point, you can have it as rho L by 4 pi epsilon h cos alpha 1 plus cos alpha 2 volt per meter along the y-axis point. If you measure along the y-axis, the electric field is given by the concept rho L by 4 pi epsilon h sin alpha 2 minus sin alpha 1 volt per meter. Volt per meter. Okay, so the above equation is satisfied for finite line. If you are going for infinite line, if you are going it for the infinite line case, then you will be having alpha 1 and alpha 2 will be equal to 0. You can see in the diagram here. You can see in the diagram alpha 1 and alpha 2, that value will be equal to 0 if you go for the infinite case. Only for finite case, we have alpha 1 and alpha 2. Okay, so for the infinite case, that value will be 0. So we are substituting that value here. Instead of alpha 1, 0, alpha 2 is 0. So cos 0 is 1. Here also we have cos 0, it is 1. So 1 plus 1 will be having just 2 there. So Ex will be. So Ex will be rho L by 2 pi epsilon h. Here you don't have the y component. So you will be having Ey equal to 0 there. Ey equal to 0 there. Okay, so Ex equal to what we will be having along that Ey equal to 0 and Ex equal to rho L by 2 pi epsilon h cos alpha. Okay, if the case is infinitely long, the total alpha it will be getting to 0. So Ex divided by rho L by 2 pi epsilon h. The electric field on the y-axis it will be 0 there. Okay, so for infinite line case 2 is very, very important because with that only more number of problems will be asking in the gate questions. Okay, so Ex equal to rho L by 2 pi epsilon h. Ex equal to what we will be having? Rho L by 2 pi epsilon h. Where epsilon is called as the permittivity of the material. And h is the distance between the line charge and the point where we are going to find the electric field. Okay, so we can see a model problem relating with that one. You can see this. A uniform line charge, infinite in extent, we have with rho L equal to 20 coulomb per meter. Okay, it is actually microcoulomb. There is a mistake in the printing mistake. It is 20 microcoulomb per meter, which will lies along the z axis. So we have to find the electric field at 6, 8, 3. 6, 8, 3. Okay, so what is that electric field formula due to infinite line charge? Just now we have seen rho L divided by 2 pi epsilon h. Rho L divided by 2 pi epsilon h. Okay, so here h value they are not given straight away. They are given in terms of points. So first we have to find out them in terms of the vector form, and finally we can reduce them into the normal scalar form. Okay, so here you will be having the formula is rho L by 2 pi epsilon naught r into r. So instead of h here you can use r into that AR vector. Okay, so here having that epsilon r value as 1. They have not given epsilon r value, so assume that value as 1, you will be getting epsilon naught here. You will be getting epsilon naught. Now we have to find out r vector and modulus of r vector so that we can find out AR vector. So to find out r vector, we are in need of 2 points. One set of points, what they are asked us 6, 8, 3. What they have given us, 6, 8, 3 there for set of points. We need another set of points. For that, they are given the clue. The line intensity is along the z axis. When the line charge is along that axis, and that axis you don't have the electric field. So what's the coordinate we have to mark here is 0, 0, 3. That's what I have marked in red here. You can see that one. The coordinates for line charge is actually it is 0, 0, 3. So why I have substituted 3 here? We have to find out the electric field at 6, 8, 3. And the problem they are given the clue when the line charge is along z axis. When the line charge is along z axis, at that point you don't have the electric field. So you will be getting 0, 0, 3 there. We have to cancel out the 3 here. To cancel out the 3 here, I am substituting 3 for the line charge also. Okay, so coordinates for line charge is 0, 0, 3. So that r vector equal to, you will be having the 6 minus 0 into ax vector plus 8 minus 0 into ay plus 3 minus 3, it will be getting for a. So r vector you will be getting into 6ax plus 8a. Similarly, the modulus of r vector, you know that concept here. If you substitute that one you will be getting AR vector. AR vector is R vector divided by modulus of R vector. Then rho L, know the concept that 20 into 10 power minus 6 divided by, so 2 pi into epsilon naught, 8.854 into 10 power minus 12 into that R value is that modulus of R value is 10. If you substitute that, you will be getting E value. You will be getting the E value. Either you can finish it off up to this one, or you can take the modulus of E vector, or you can take with the modulus of E vector. So that modulus of E vector is equal to root of 21.57 square plus 28.76 whole square. That is the final answer what will be. So this is what we have for electric field due to infinite line charge. So the next one, what we can see it is about the circular disk. So assume the CD which is full of having charges. Okay, CD is full of having charges. So at the given point, what will be the electric field because of the charges present in the disk? Okay, the CD is having full of charges. So because of the charges which is present in the disk, I am having specifically pointing one point. So at that point, what is the value of electric field? That point, what is the value of electric field? That we can determine. And this concept relates with the surface charge density. The last one, what we have seen is along with the line charge density. And this one deals with the surface charge density concept here. Surface charge density concept. Okay, so here you can see that one. Electric field due to circularly charged disk. Circularly charged disk. So for that, what will be having the concept of this one? Electric field equal to rho s by 2 epsilon into 1 minus h divided by root of h square plus r square. Root of h square plus r square. Okay, so what is that h value? What is that h value? It is the distance between center of the disk and the point. And the point where we have to find out the electric field. So I have some more along the, as I told yesterday, you can have 3-axis component in electromagnetic fields. Normally in the mathematics, you may solve with the 2-axis component, x and y. Whereas when you come for the electromagnetic field, we have to analyze in the concept with the term of 3-axis component there. X, Y, and Z. Okay, so the point may be somewhere. So what is the distance between that point and the center of the surface charge disk? That we call it as h. And capital R is nothing but radius of the disk. Capital R is nothing but the radius of the disk. So you will be having that one E equal to rho s by 2 epsilon into 1 minus h by root of h square plus r square. So simply we can say from the diagrammatic view that h by root of h square plus r square is called as cos alpha. So the diagrammatic you can clearly see about that cos component adjacent by hypotenuse. Adjacent by hypotenuse. So adjacent part is h, hypotenuse part is root of h square plus r square. Adjacent part is h, hypotenuse part is root of h square plus r square. So you will be getting this one. Instead of h by root of h square plus r square, you can have it as cos alpha. So E equal to rho s by 2 epsilon into 1 minus cos alpha. That's what we have it as E equal to rho s by 2 epsilon 1 minus h by root of h square plus r square. Now we can see the model problem related with that circularly charged disk. You can see the question. The circularly charged disk, it is of 10 centimeter diameter, is charged uniformly with a total charge of 10 power minus 6 coulomb. So what we have to find out is the electric field at the point 10 centimeter away from the disk, which is along the axis. And for your easy understanding, I have given you with the diagrammatic representation. In exam point of view, they will not give you about the diagrammatic explanation. Just for easy understanding of the concept, I have given you this diagram. So you can see the circular disk of diameter 10 centimeter. So what will be the radius? 5 centimeter. Diameter is 10 centimeter, so the radius is 10 centimeter. So that I represented R equal to 5 centimeter. Diameter 10 centimeter, radius will be 5 centimeter. The total charge, they are given Q value. They are given Q value 10 power minus 6 coulomb. 10 power minus 6 coulomb. They are given the charge value. What we have to find out is electric field at the point 10 centimeter away from the axis. That is H value also they are given. 10 into 10 power minus 2. So with this concept, what it is understandable is they have given you H value and R value. They have given you about H value and R value. So in the problem, what we need about the rho S value. Epsilon is constant, 8.834 into 10 power minus 1. Since the medium is air medium, epsilon R is 1. If you know about the rho S, you can easily find out the electric field at that point. But they are not given rho S here. Instead of rho S, what they are given? Charge, Q value. What they are given is charge, Q value. So Q equal to 10 power minus 6 coulomb. So you can see the problem here. We will be having En rho S. So we have to find out En rho S. So E equal to rho S divided by 2 epsilon into 1 minus H by root of H square plus R square. We know the H value and R value. If we substitute that one, we have to go for R rho S. So rho S, how we can find out? Q by ds. That is pi R square. Q by ds. That what will be having as pi R square. Area of the circle. So R value you know about that one. Pi into 10 power minus 2. So if you substitute that one, you will be getting rho S value as 1.27 into 10 power minus 5. Then substitute the rho S value here, you will be getting electric field. E equal to 759.61 kV per meter. So this is one of the concepts what we will be having dealt with that surface charge density. So the next one you can see with the infinite sheet of charge. So for the infinite sheet of charge, what is the electric field intensity? So far we have seen with the two cases. One is with the line charge, then second one is with the surface charge. If the line is having full of charge, density full of charge density rho L, what will be the electric field? First one we have find out. Then second one, if the disk is having circular surface disk is having charge density of rho S, what is the electric field nearest to that point? Now we have infinite sheet of charge. The diagram we can see the infinite sheet of charge, which is having the charge density of rho S. So at this point, what will be the electric field? At this point, what will be the electric field? That you can find out using this formula. E equal to rho S by 1 minus cos alpha. So here from the circular dark charge density, we can have the concept. Here that alpha equal to 90 degree. What you have to substitute? Alpha equal to 90 degree. Okay. So if alpha equal to 90 degree, cos 90 equal to 0. So you'll be getting E equal to rho S by 2 epsilon 1 minus 0. Okay. So you'll be getting E equal to rho S by 2 epsilon volt per meter. So if you know the charge density of the infinite charge, you can calculate the electric field intensity at that point. Electric field intensity at that point. Okay. So the next one we have it as a flux density. So far we have seen about the electric field intensity. The next one what will be having as the flux density D. Simply we can say the flux density, electric flux density is electric flux per area. Electric flux per area. So the total electric displacement when you move the point from one charge to another charge. When you move the charge from one point to another point, you will be getting that electrical displacement, what we call it as electric flux. Normally it is the scalar field. So the density of electric flux, what we call it as electric flux density, capital D. Okay. So normally the electric flux density is the vector field. It is a vector field and it is measured in coulomb per meter square. Okay. So for the sphere surface area, you will be getting D equal to flux per 4 pi r square. From Faraday's experiment, we can have total electric flux equal to total charge. So instead of flux, I can substitute Q there. So what you will be getting D equal to Q by 4 pi r square. Already know about electric field. Electric field equal to Q by 4 pi epsilon r square. Q by 4 pi epsilon r square. Electric field E equal to Q by 4 pi epsilon r square. Whereas D equal to Q by 4 pi r square. So we can relate these two. D equal to epsilon E. So from the electric field equation, we can write D and electric field as D equal to epsilon E. Okay, so the electric field intensity is the product of permittivity and electric field intensity. It's the product of electric field and permittivity of the medium. So a very famous concept that electric flux density D equal to epsilon E. D equal to what will be having? Epsilon E. Epsilon is the permittivity of the medium and it has a subdivision formula as epsilon naught into epsilon r. Epsilon naught into epsilon r. So now the famous law, you know about that Gauss law concept there. Okay, so what is the Gauss law states that the total electric flux passing through any closed surface, it is equal to the net charge enclosed by the surface. So the total electric flux passing through the closed surface is equal to the net charge enclosed by that surface. So that's what I have shown in the diagrammatic representation for that one. We have cloud of point charges, that is Q, that is equivalent to the net charge flux, the net flux. Okay, so from the Gauss law's experiment, we can say that fluxes charges is equal to surface integral of flux density into ds. Surface integral of flux density into ds. Or volume integral of volume charge density into dv. So these are all the famous formulas what it will be useful while solving the problems. So by Gauss law, we can resolve this problem. Surface integral of d into ds and volume charge density into rho v to dv. Volume integral of rho v into dv is equal to charge. That is also another formula. Then we can say the surface as the Gaussian surface. So these are all the conditions for the Gaussian surfaces. We can say surface is a Gaussian surface when the surface is closed. When the surface is closed, we can say the surface is the Gaussian surface. And at each point of surface, either flux density is normal or tangent to the surface. At each point of the surface, what happens? Either D is normal or tangent to the surface. And mostly the flux density is constant over the part where the D is normal. So we are saying that D is normal now over that part, the flux density will be remaining constant there. About the thing what we have seen about the Gauss law. Total electric flux equal to total charge. Total electric flux equal to the total charge. And these are all the applications of Gauss law. By applying the Gauss law, we can find out electric field due to infinite line charge. So far, we have seen the infinite line charge derivation. The same concept we can derive with the help of electric field also. Okay, the next one we can find electric field due to coaxial cable. We can find that electric field due to coaxial cable using this Gauss law. And we can find the electric field because of the single shell of charge. If you have single shell, if you have full of charge, how much electric field is present near that charge? We can find out using that Gauss law. Similarly, we can find out with the help of concentric shell of charges. So here the simple example what I have given you for the single shell of charge here. So a single shell of charge having the Q as the charge and the distance radius as A. And the outer part what we have is the R. So at R equal to A, we have electric field as Q by 4 pi epsilon A square. At the outside part of the sphere, you will be having E equal to Q by 4 pi epsilon R squared. Okay. So similarly, we can obtain for the concentric cell of charges. If you have two concentric cell of charges, here explanation given with that two cell of charges, concentric cell of charges with Q1 and Q2. With Q1 and Q2 there. Q1 is of inner radius A and Q2 is with the outer radius B there. Here also with R equal to A and R equal to B, we have the constant. Okay. So that E equal to at A, R equal to A, the electric field is given by the formula Q1 divided by 4 pi epsilon A square. At R equal to B, the field intensity is given by Q1 plus Q2 divided by 4 pi epsilon B square. And this is a simple problem related with that total charge. With the Gauss law problem, you can see that one. We have to calculate the total charge enclosed by the cube of 2 meter. 2 meter sides centered at the origin and with the edges parallel to the axis. And the electric flux density over the cube is E equal to 10x cube by 3 AX coulomb per meter square. So the problem is they are given with flux density and we have to find out Q. They are given with flux density D, we have to find out Q there. So how we can relate the flux density? You know about the divergence theorem concept there. Divergence theorem concept. So surface integral of D dot ds equal to volume integral of del dot D into dV. Surface integral of D dot ds equal to volume integral of del dot D into dV. And also you know about the concept that del dot D is nothing but rho V. Volume integral of, here we have written no. Once again, I will show this one. Here we have written no, rho V into dV. So this rho V is nothing but del dot D. Divergence of the electric flux density is what we call it as volume charge density. Very, very important concept. Divergence of, so this and all the statement. While studying the electromagnetic field theory, to study the formulas as a statement. Okay, that's and all very, very important. They will be asking you in terms of that part. You can see this one here. You can see this one here. Okay, so volume integral of del dot D into dV there. Volume integral of del dot D into dV. So rho V equal to what we will be getting? Del dot D. So don't think where it comes del dot D. So by divergence theorem, we have this one. Okay, surface integral of D dot ds equal to volume integral of del dot D into dV. Okay, so this volume integral of del dot D into dV is nothing but charge there. Nothing but charge there. Also from Gauss law, we can find out that one. Double integral of D dot ds equal to Q. If you substitute that also, it will be fine. Then del dot D means divergence. And seeing the system, you can find out it is a Cartesian system. For this one day, I have taken you in the last class the very important concept of different coordinate systems, Cartesian, cylindrical, and spherical coordinate systems. Okay, so the divergence, so by seeing the vector, we can see it is the AX vector, so it corresponds to the Cartesian coordinate system. So the divergence we are applying with the Cartesian coordinate system, and we are finding out system. Similarly, dV formula, it corresponds to the Cartesian coordinate system. Now apply that thing, and if you take the volume integral, you will be getting 80 by 3. So this how can shortly find out this kind of questions they may expect you in the gate parts. Okay, where we are relating new formulas there. So they are given with electric flux density, and we are asking to calculate charge. There is no direct link with this one. They are relating with the divergence theorem, and if they are taking that one. So this is about the normal thing what we will be having. So the next PPT that will take a moment, I will be sharing about the potential. So far we have seen about the electric field intensity. Now I will be sharing about the potential part. So I think it is visible to you. You can see about that. Next one, potential. So far we have seen about the electric field concept. So far we have seen about that electric field concept. Next one, I am showing you about the potential. Okay. So what is the potential? It's nothing but simply we say it is the potential difference between the point and the reference point where it is chosen as where the potential is zero. So we are moving the charge from one point to another point against the electric field. Against the electric field. Okay, so from P1 to P2, we are moving the test charge against the electric field. What will be having the term? Okay, so you can see that simple concept there. Potential and electric field are related by the formula V equal to minus integral of E dot dv. Since we are moving against the electric field, the charge is moved against the electric field, we are inserting the minus sign there. Okay, so this is a very important concept there. So potential and electric field are related by this formula. Okay, V equal to minus integral E dot dl. Where E is the electric field and dl is the differential length. And when you represent in the normal form, so far we have seen with the integral and differential part, simply if you relate with the potential and the electric field, V equal to E into R. Simply we can say it as E into D, electric field into distance. Okay, or to obtain with the formula, we can say that one E into R. So V equal to Q by 4 pi epsilon into R. So the electric field is Q by 4 pi epsilon R square. Q by 4 pi epsilon R square you will be getting. For potential, you will be getting Q by 4 pi epsilon R. So most of the students, they will be confusing with the formula of electric field and potential. Okay, so for electric field, you will be getting with Q by 4 pi epsilon R square in the generalized formula. Whereas for potential, it is only with respect to R. So we can say here potential and the distance are inversely proportional. So later on, we'll be seeing about that concept one by one. Later on, we'll be seeing about that concepts one by one. Okay, so you can see a model problem here. To obtain the know concept importance of the potential, you can see about the model problem. Okay, so we have 2 point charges. One point is on 0, 0, 0.1. Then another point is minus 1.5 nanocoulomb. It is at 0, 0, minus 0. Both are in free space. So what is the potential at 0.3, 0, 0.4? That we have to find out. Here you will be getting 2 potentials. Because of charge Q1, one potential. And because of charge Q2, you will be getting another potential. So if you add the 2 potential, that will be the final value. That will be the final value. So individually, we have to find out V1 and V2. Individually, what we have to find out? V1 and V2. And later on, we have to add that both the voltage. Later on, we have to add about that both the voltage, the potential. And you might ask here, why we are not going for the vector part here. Here also they are given only with the points. We are taking only the modulus value. We are not going with the R vector and all the AR vector and all, because the potential is the scalar field. Electric field is always the vector, whereas potential is always the scalar. Potential is always will be having with the scalar part. Okay, so in the problem they have given you with the potential V point also. So straight away we are going with the modulus value and we are substituting it and finding out the V1 value. Similarly, for Q2, we are finding out V2. Just now I told you about the formula of V1. Okay, V equal to Q by 4 pi epsilon R. So V1 equal to what you will be getting? Q1 by 4 pi epsilon R1. So now V1 and V2, you have find out. If you substitute that value, you will be getting the total potential. So the total potential equal to V equal to V1 plus V2. Okay. Then this is the basic relation, one of the relations with respect to electric field and potential. Okay. So E equal to minus del V. So this equation also you can study as the statement that what is electric field? The negative gradient of potential. Negative gradient of potential is nothing but electric field. So in the last session, I have told you about del V, about gradient divergence and curl. Gradient divergence and curl. Okay, so these questions and all definitely in gate part they will be asking me in 1 mark. What is the negative gradient of potential? Flux density, field intensity, charge. Like that, they will be giving you more answers. So the negative gradient of potential is nothing but electric field intensity. Always E and V will be with the negative sign. That you should keep it in mind. Now, not only the gradient of electric field potential, negative gradient of potential. Because we are moving the charge from one point to another point against the electric field. Okay, so you will be getting with the negative sign. E equal to minus del V. So in the problem, if the potential is given and you are asked to calculate electric field, you have to use this formula, E equal to minus del V. And similarly, in the problem, if they given you electric field and you are asked to calculate potential, you have to use this formula, V equal to minus integral of E dot dS. So both the things we will be seeing you now. Sure. So these kind of problems they may be expecting in the university gate parts. You can see this one. Given V equal to 120 sin theta by R square in free space. Find the electric field intensity at R equal to 3, theta equal to 60, phi equal to 25 degrees. Find V at that point. As I told, so yesterday, the last session, what we have seen is about the basic coordinate systems. So I have told you the importance of different coordinate systems. So don't think only Cartesian coordinate system exists. There also exists cylindrical coordinate system and spherical coordinate system. Okay, in exam point of view, they can ask they will not ask alone with the Cartesian, because the Cartesian will be very simple concept. Normal x, y, z concepts, what we might have studied is very simple. Okay, so in the exam point of view, they may also ask with the spherical parts. So this problem, they are given with r, theta, and phi. What this problem relates with? Spherical coordinate system. This problem relates with the spherical coordinate system. So what they are given, we have to find out V. Straight away, if you substitute r, theta, and phi, you can find out V there. That's the second part that we state. The first part, what they ask, electric field intensity, E. They are given potential V there. What I had told, if potential is given and if you want to find out electric field, what you have to find out? Formula we have to use E equal to minus del V. E equal to minus del V. Del V means gradient. First we have to find out del V, gradient of the potential, and if you substitute minus sign, you will be getting electric field. So first I am finding out dV, del V here. And also in the last session, I have taken you about for a gradient also there exists different coordinate system, Cartesian, cylindrical, spherical coordinate system. So the formula will not be same for all the coordinate system, it will be different. So the for spherical coordinate system, what is the formula for del V? So dou V by dou R into AR plus 1 by r dou v by dou theta into a theta plus 1 by r sin theta dou v by dou phi into a. Dou v by dou phi into a. So we have to apply that one. So you have to partially differentiate. With respect to r, you will be getting one answer, and with respect to theta, you will be getting one answer. There is no phi here. So the third part will be getting 0 here. And we have to resolve the components and minimize the components thing, and you will be getting del v. After that, if you put minus sign, it is minus del v. So that is the E value. If you want in modulus form, you have to take in. So the above minus del v is nothing but electric field. It is in vector form. If you want in the modulus E value, it will be in the scalar form also we can obtain. You can find the electric field in the scalar form or in the, mainly in the vector form you should have. If you need only the magnitude, then we have to take the modulus. Okay, and the thing here, you can see this thing. So that the E vector is irrotational and find its scalar potential. So where you can go for the concept of irrotational from the concept of curl. From the concept of curl. So what is the condition for irrotational? If you take the curl of the vector and if we are getting the answer as 0, then we can say that vector corresponds to irrotational. That vector corresponds to irrotational field. Okay, so for curl of vector, what we should obtain? Del cross E equal to 0. For curl, what we should have that? Del cross E equal to 0. Okay, so above problem is given along with the Cartesian coordinate system. Ax, Ay, and Az. Ax, Ay, and Az. So you will be getting del cross E equal to 0. That we have to find out. So that we have to show that del cross E equal to 0. So first I am going for del cross E. Curl of the vector. Since it is Cartesian system, the formula will be simple. Just Ax, Ay, Az, dou by dou x, dou by dou y, dou by dou z. Then already you know about that x coefficient, y coefficient, z coefficient. Substitute that one and find out the answer. Here we are getting it as 0. So we can say the vector is irrotational. Then second part, what they are asking is we have to find out the scalar potential. What we have to find out? Scalar potential V. Okay, so in scalar potential V, what we have to find out? V there. So what's the formula? They are given with electric field and we have to find out potential V. So V equal to minus integral E dot dl. V equal to what you will be having? Minus integral E dot dl. Now E value you know here. How to find out dl value? We have to see what type of system, whether it is Cartesian system, cylindrical system, or spherical system. If it is a Cartesian system, dl formula will be different. For cylindrical and spherical also it will be different. The dl formula, we are writing it for that. Since the problem is given with the Cartesian system, for dl, what is the Cartesian formula that I have taken? Okay. So before going to study with the electromagnetic field, be thorough with the 3 coordinate system. It is very, very important for you. Because the 3 coordinate systems will be helpful in all the area of electromagnetic field. Okay, we cannot adopt the same Cartesian system formula for all things. Okay, so now we are doing with the E dot dl formula, the dot product. You know about the dot product. Like products only will be getting 1, unlike products it will be getting 0. Then we are going that one and we are taking the integral part and we will be getting the V value there. V equal to minus 6xy square plus zx constants. Okay, so that we are so far we have seen about the basic potential and about that electric field and potential part. So the next one, what we can go through about the electric field and equipotential plots. So we say the surface as the equipotential surface when the potential is same everywhere. So you see that the diagram, you can see that one. I am placing a point on R1. Okay, it is showing one potential. Then I am moving to the left hand side. It is also at that point also it is showing the same potential. And at the downwards I am coming now. There also it shows the same potential. So I can circle that part. I can circle that part there. Where and all I am getting same potential, I can circle that part and that the surface, what we call it as equipotential surface. That one, what we call it as equipotential surface. So here in the diagrammatic view, I have shown for three cases: equipotential surfaces R1, R2, and R3 for different things. Okay, and we can say that potential and distance. Okay, so since the points are the distance R1 from origin is same, we say that surface is called as an equipotential surface. Now another concept we have equispaced surface. The last one, what we have seen it as a equipotential surface. Now equispaced surface. So what is that equispaced surface is? In the diagram we can see that if you have change in del V is constant throughout the surface, then it is called as equispaced surface. So clearly we are represented with the diagrammatic view. So in the first one we have uniform distribution of charges. In the second one we can see with the non-uniform distribution of charges. So the statement clearly you see that if we maintain change in potential between various equipotential surfaces constant, then such surface is called as equispaced surface. So there is a difference between equipotential surface and equispaced surface. So if we have change in potential is constant throughout the surface, that is called as equispaced surface. Okay, and you can see that one here also we can see that concept that potential and distance are inversely proportional. V equal to Q by 4 pi epsilon R here. Okay, if you move from the origin, the potential will be getting reduced. So at the center point of origin, you will be getting with that more amount of potential. Since we have that formula that V equal to Q by 4 pi epsilon R. 4 pi epsilon into R. R is the distance. So if we move from the origin, the potential will be getting reduced there. The next one we can have with the utilization factor. So this is all the easy concept what you can have with the thing. So utilization factor, or otherwise what we call it as the field utilization factor. So it is the ratio of mean electric field to maximum electric field. Mean electric field to maximum electric field. Okay, so if you want to find out the electric field ratio, the utilization factor, we can go for this one. What is the average electric field determined by the maximum electric field obtained on that material? If you take for the parallel plate capacitor or for anything. Okay, so you will be getting with the meter. Similarly, the last thing you can find out that electric field due to circularly charged disk, infinite line, all these concepts you have seen. Similarly here. So what is the potential due to circular disk? What is the potential due to circular disk concept? Okay, so for the circular disk, what is the potential due to the circular disk? So if you know the electric field due to circular disk, from that we can extract about that potential. Okay, so E equal to rho S by 2 epsilon into 1 minus H by root of H square plus R square. This is the thing we have obtained for electric field due to circular disk. So that cos alpha we can say it as H by root of H square plus R square. Okay, so we apply that concept here, and from that we can find out the potential. Rho S by 2 epsilon into root of H square plus R square minus H. You know about that H and R. H is nothing but the distance between the center of the disk and the point where we have to find out the electric field. And R is the radius of the disk. And R is the radius of the disk. R is the radius of the disk. Okay, So we know about that potential. Then about the dipole. So we know about concept of the dipole. Dipole is nothing but two equal and opposite charges separated by the small distance. We have plus q and minus q separated by a small distance. What we call it as electric dipole. Okay, so the product of charges and their distance is what we call it as dipole moment. M. Dipole moment M is nothing but product of charges and the product of charge and the distance. Okay, so the electric dipole, it will be, you can see the diagrammatic representation of the term. Electric dipole. Okay, we have q and minus q, and if you want to find the electric field at this point P, what will be the dipole moment? Electric field at this point P because of this dipole. It is given by this formula V equal to m cos theta divided by 4 pi r square. M is the dipole moment, okay, and r is the distance between them. And theta is the angle of representation, separation between the two. So the statement is very, very important. Potential due to dipole is directly proportional to dipole moment and inversely proportional to square of the distance. Inversely proportional to the square of the distance. Okay, so that I had told you, please study the equation as a statement there. Okay, so potential, because of a dipole, if you are getting the potential, that value will be directly proportional to the dipole moment and inversely proportional to the square of the distance. So in the later on classes, we will be seeing about that conservative field, and we can go for the Poisson's and Laplace equation, and we can move on to the next concept called the important concept called boundary conditions. Boundary conditions, and we can see about the capacitance and all these things. Okay, students. So thank you. We can see it on the next session. Thank you.